Welcome back, ladies and gentlemen. We've got day 9. So we're going to talk about electromagnetic radiation, and we're talking about first the history. So there's two kind of things that happened. Right, most of our history is from 1800 on for chemistry here. And the first thing on the left here, atomic spectra. So what atomic spectra? We'll learn this soon. All right, if you looked at the colors of a rainbow, they're red, right, orange, yellow, green, blue, indigo, purple, violet, right? That's the whole color. So if you see a rainbow, you see the sunlight through a prism, you see all those colors. When you look at atoms, atoms have specific colors, right? They have specific colors that they show. They don't show, right, every color. They only show you specific colors. And that was a question. Why is that, right? Okay, so we observed that. And these are atomic fingerprints. Okay, and there's several people who spent their careers trying to figure this out, and they made lots of good progress. It's wonderful. The other side of the house is atomic structure. And we know some of these things. We know protons. We know neutrons. We know electrons. And we talked about some of the people who found what these things and what atoms are made of is important. 1803, Dalton came up with the atom, atomic theory, right? And then Thomson came up with the electron. Millikan, he did his famous oil drop experiment, and he got the electron charge. Rutherford, the gold foil, he came with the nucleus. All right, so we're trying to figure out, lots of people are trying to figure out matter and what it was, okay? All right, and then there's a few guys that came up with quantum theory. All right, so after they took all the, like, spectroscopy and whatnot from these atomic spectra to the atom structure itself, right? That lead to, so both of these led to quantum theory. So Planck, what Planck do? Planck, black body, radiation, and he has his constant. Einstein, he explained the photoelectric effect. Right? Haas, Bohr, Rutherford, all these guys explained hydrogen line spectra. He explained this thing right here for hydrogen. And then that led to the quantum mechanical model of the atom, which led to a boom in the 2000s. Right? 1920s. Right? And so what we want to do is when we go through this, what's very important for us, is we want to know how the structure, decomposed matter, determine the properties of the matter. All right? Okay, and we know that electrons determine many of the atom's chemical and physical properties. We know that. Right? Why? The electron occupies the most space. So we're going to try to study electrons, all right, first. And we're going to digress a little bit to go into energy and whatnot. But we're going to build up how we can study the electrons, where the electrons are, what they're doing, and then that goes into how we can predict what's going to happen when we mix different atoms together. So energy. A lot of times books in the 100 level, describe energy as the capacity to do work or transfer heat. Right? So there's two types that we've talked about. Kinetic energy. All right? Think motion. And kinetic energy is equal to 1/2 the mass times the velocity squared. All right? So that's kinetic energy. And there's different types, kind of, but that's the main kinetic energy. Thermal energy is a kinetic energy. That's what we really care about a lot. And that's the interstate energy associated with the random motion of atoms and molecules and the subatomic particles that compose them. Potential energy, think position. Right? Potential energy, you get basic physics class, mass, acceleration, typically due to gravity, and how high it is, right? Jumping out the first floor window, not that big of a deal. Second floor, more of a big deal. Third floor, even more of a big deal, right? Okay, and so that's because you walked up the stairs, you gave yourself potential energy, and when you jump out and fall, you transfer that energy from potential to other forms. Now, chemical energy is what we really care about. Chemical potential energy. And that's stored within the structural units of the chemical substances. Basically, how they're put together, the bonds, and how it works. And then there's also electrostatic energy your book mentions. That's a potential energy that results from the interaction of charged particles. All right, so now we have the law of conservation of energy. It usually pops up now. There's actually a law of conservation of mass and energy, all right, because of this famous, all right, a lot of people think Einstein, think that one, right? But where I live, how I'm getting my electricity is this way, right? We're using nuclear, okay? Now, the unit of energy is the joule, right? And a joule is a Newton meter, right? So, kilogram, meter squared, second squared is a joule. And so since that's a joule, whenever we're in joules, make sure our mass is in kilograms. Now, the whole point of this is when we talk about energy, we talk about energy's capacity to do work or transfer heat. And one thing that a lot of us notice is that there's different types of energy. There's, again, nuclear, there's electrical energy, we can do fire, right? We can do thermochemistry, However, there's another one that we all feel, and that's if we go outside, the sun has energy. And so light, right, also has energy in the form of joules. All right, so let's talk about light. Light, right, any type of electromagnetic radiation is a type of energy, right? It has what's an oscillating electric and magnetic field. And so if you think of a wave, right, here's the spectrum, right? If you think of a wave, what is a wave? So y-axis, x-axis, right? A wave, right, it goes up. Oh, wow, that was not supposed to happen. Let's make this a little longer. All right, let's try that again. Wave goes up and down. And now it keeps on going, right? It should keep on going and keeps going. Right here, where that wave ends, right? That's the length of the wave, right? If you math class, like y equals sine x or y equals cosine x, right? You graph those on your calculator. If you played with those before, that's what we're talking about. That's a wave, all right? Now, if you notice a couple of things about this wave, there's the height of the wave. All right, this is the amplitude. All right, that's how high it is. The length of the wave, right here, or wavelength, they use L for, which is Greek. It's lambda. All right, that's how long the wave is. Okay. So if we go, what is oscillating electric and magnetic fields? One direction would be the wave of where it goes up and down of, let's just say, the electric component, and then horizontally, right, 90 degrees, you'd have the same wave going magnetic. So there's like two waves at once. One's going up and down, one's going left and right as they go through. Think of it that way. All right. And the spectrum of electromagnetic radiation, we see this small, tiny bit right here. Okay, so if you look at what happens, low energy waves on the right here, this picture, you got 100 meters. All right, there's actually kilometer wavelengths out here, okay, because it just keeps going. There's no end to it. Radio, right, AM, FM, right, TV used to be radio. Radar is in here, all right. And you got infrared. Think of it as in the far red because red's on this side. All right, you got infrared. This is actually right here is a micrometer. Right? So microwaves are in there. Our visible, there's our Roy to G Biv going kind of backwards for us. And then you have ultraviolet, X-rays, gamma rays, you have cosmic rays, right? And if you notice, there's low energy to high energy. Okay, so they have different colors, look like they have different energy, and we're going to get to that. So light travels at that exact speed in a vacuum, 2.99792485, or 2458, excuse me, times 10 to the 8th. And lambda, right here, is the wavelength. This is nu. All right, so this is the frequency, which is nu, Greek letter nu, right? And it's in cycles per second, 1 over seconds or hertz. And wavelength in meters. And c is your speed. So the speed of wave, wavelength times frequency. So now if we look at this equation, if lambda gets bigger, frequency has to get smaller. And if frequency gets bigger, wavelength has to get smaller, right? Because they equal a constant speed of, we'll use 3 times 10 to the 8 most of the time. All right, so with light behaves a little bit differently than most things. All right, so we're going to go into the history here. Planck, right? Why do heated objects emit radiation, and why does the color change? So if you look here at this fun graph, we have wavelength in micrometers and then the intensity. And what happens is that's the temperature that we're trying to make, and they got this thing called lambda max, which is basically, think of it as a color you can see. And as we heat up, as the temperature gets hotter, what we see kind of goes from red to orange to yellow. It goes up. But here, it stops. And then it comes down, and we don't see any UV. We see infrared. We see visible. We don't see any UV. That was called the UV catastrophe. All right? And so a black body. What is black body? So a black body right, is a body that absorbs all of the light or electromagnetic radiation that falls on it. So a good approximation to a black body is a cavity with a tiny hole. So if I had something that kind of like that, little cavity, and light came in, and then it started reflecting around. Oh, we don't want to do that. We want to do this. It started reflecting around. Right, and eventually dissipate, right? So now, when the cavity is heated, walls emit light. All right, this is because they're made of atoms, right? The atoms vibrate or oscillate, and then they emit light, all right? And then we're going to have a tiny portion escapes through the hole, right? And then the radiation or light emitted is a function of temperature only. All right? And so what do we get from that? We get, all right, that atoms vibrate. They can only vibrate with certain energies. Only certain energies, right? Well, this Boltzmann, so Boltzmann distribution, there's something called K, a Boltzmann constant, it's lowercase k. There's a special number called Avogadro's number. When you divide them, you get 1.38 times 10 to negative 23rd joules per Kelvin. Small number, all right? And so then, great. We can do this. We're not going to do this because we're not going to even come close to that math. What's important with this? Planck's constant, H, 6.6 times 10 to negative 34. That is a small number. Think about that's a very small number, all right? I mean, 3306, that's tiny. Very important number. Hugely important number, okay? And so Planck did his work, and the outcome, basically, all we want to know is that he came up with this constant for our purposes right now. If you're going to go higher up and understand more, and great, right? But for our purposes in this course, just H is 6.626 times 10 to negative 34 joules times seconds, and that's that. As we continue, Einstein, all right, he had the quantization of radiation, all right? He explained the photoelectric effect. So we're dealing with things that it just doesn't make sense, right? We deal with macroscopic objects. Well, you and I deal with cars, golf balls, baseballs, softballs, basketballs, volleyballs, right? Balls, we talk about, objects we see, touch, feel, like if you throw something, right? And we deal with these things, all right? All right, well, what's the photoelectric effect? All right, what is the photoelectric effect? Do I have a picture of the photoelectric effect? I do not have a picture of that in here. So basically, the photoelectric effect, we have a piece of metal here. That's an arrow. Let's try a piece of metal. I have a piece of metal. And that piece of metal has two wires. All right, or a wire coming out of it. And it has, let's just say, I don't know, voltage source, and it has a voltmeter, and then another electrode here, okay? And this is enclosed. If light comes in, if the certain UV light comes in and hits, electrons can go and complete the circuit, all right? So basically, that's weird, but it's usually UV only, okay? It's not other lights, okay? And so the assumptions would be, we'd have two assumptions with this if we were doing this, all right? Brighter, all right, or more intense light right, should eject electrons with more kinetic energy. And 2, photoelectric effect should occur at any frequency or any wavelength, so to speak. So now, let's give an analogy we do. You know, myself, I'm around a lot of Marines, all right? And a lot of these Marines, they take care of their vehicles amazingly well, right? If you get in their truck or their car, you're getting it dirty, right, with your shoes. That's how clean they keep it inside and out. And they wash their cars all the time. So I'm assuming a lot of you wash the cars. If you wash the car, I wash the car, right? What do we use? Well, we can use, most of us use a hose with a nozzle on. That kind of makes sense. Maybe you use a power washer with the appropriate tip, right? Nobody uses a fire hose from the fire hydrant, okay? And why don't we do that? Well, obviously we blow out the windows, and that would be very counterproductive for washing the car. Could we use a super soaker? You could. Could you use a little tiny pump finger squirt gun? I guess you could. Would you ever? No. Maybe you're paid $100,000 to do it. Maybe you would, right? But no, you're not going to do that, right? And we use the hose or the power washer with the appropriate nozzle to wash the car because the more water it hits, the better it rinses things off, right? Right? That's more intense water, does a better job, okay? That's not how light works, right? The analogy of washing the car, if you used red water, right, or infrared water, you could blast your car with a fire hose of infrared water and nothing would happen. But if you take that little pump squirt gun, right, of UV water, and you hit the window, boom, window's gone, right? And so it's not the same as how our macroscopic world is, right? And what Einstein figured out is that the energy of the electrons depends on the frequency, not on how bright it is, which is really weird, okay? Okay, so what Einstein found is that the energy of a photon is equal to Planck's constant times the frequency. Energies in joules, and of course Planck's constant is 6.626 times 10 negative 34 joules times seconds. All right. So if you increase the intensity, you get more electrons, but you don't get more energy, right? Which is weird for us. And so what this comes out to is that light can act as both a wave and a particle. All right. And they are characterized by energy, wavelength, and frequency. All right, so if I take our two constant, speed of light equals wavelength times frequency, and energy equals constant times frequency, notice that there's something in both. All right, and so if I rearrange the speed of light divided by the wavelength equals the frequency, I can plug in this for nu over on the right on the other equation, which would give me energy equals constant over wavelength. And so in this video, we're going to end with the fact that energy of a photon is equal to constants that don't change over the color. Right? So what I want you to take away from this is that each color has a different energy. And that's very important to the colors we observe, especially when we talk about the atoms next. All right? And so that's it for this. We're going to have another video on some examples of using these equations, and that we'll move on from there. Well, I hope that works for you guys. Let me know if you have any questions, and we'll see you next time.